So I'm going to talk about some work that we've been doing at Texas A&M having to do with trying to understand the symmetry energy of the nuclear equation of state. So since I know that's a little different than some of the other things we've talked about here, I'm going to do a little bit of an overview and a motivation, talk a little bit about the symmetry energy, explain the experiment, show you just some real quick overview of the detector that was used. We'll talk a little bit about transverse flow, the measurements that were made, the theory that we ran to compare it to, and then put it in context with some other measurements. Okay, so I always thought, we all know that we can describe the nucleus as a liquid drop, and in terms of it being a cold, normal density nucleus, we can understand the binding energy or the mass. And we realize, obviously, we talked earlier this week about how as you go further away from N over Z, that doesn't work so well. But as long as you're staying near the value of stability, normal nucleus, cold nuclei, this describes it quite well. So when we talk about the equation of state, what we're trying to do is look at what happens to that binding energy as you change the density, okay, or you change the pressure. We're looking at an equation of state. And so I kind of put this graph in here just to give you that idea. There's a minimum in that curve of the energy with density, and so that's this is still now for cold nuclei that are near the value of stability, but it's understanding this curve that we're really trying to get at, okay? And then trying to understand this curve as you move away from N equals Z nuclei is in particular what we're going to talk about here today, okay? So why is it important, okay? So it's important because this nuclear equation of state that I talk about is the thing that has to describe everything from atomic nuclei and some of the structure effects and neutron skin thicknesses to what kind of matter exists inside of a neutron star. And so it's one equation of state that really has to describe it all. So we really need to understand, because we can't do something that answers something locally here and doesn't explain life there, because it's the same thing that has to go over this whole range of physics. Okay, so another way to look at that was something put together by Andrew Steiner a few years ago that really says, trying to really put the context of how important it is to understanding the symmetry energy, both in terms of our basic nuclear science and the sort of things we can measure in the lab, from nuclear masses and skin thicknesses, giant resonances, flows, multifragmentation, the importance of nuclei, quark stability, and red beams, and how these things depend upon the isotopy independence of the strong interaction. And from all of these measurements, we can get out a many-body theory, and we can understand the symmetry energy, which then becomes really important to, and an input to all of this nuclear astrophysics, okay? And so it really is very fundamental to be able to understand this. Ani asked the question earlier this week about, how did we make the nuclei from iron to lead, or iron to uranium, or whatever she said. All those things out there, all those elements. I'm a chemist, that origin of the elements thing. And she showed us how nicely that much of that is happening very far from stability, and we need to understand what's happening very far from stability. We need to understand how those nuclei are made, how those elements are made. And so understanding this symmetry energy gets this equation of state away from where we understand it pretty well, which is by the value of stability, to extend it out to these very neutron-rich systems. Okay, so I'm going to just flip through these. I had a couple slides in terms of looking at the mass radius relationship of neutron stars, the input to how the symmetry energy input, whether it's a stiff or a soft dependence, gets you different cooling of neutron stars. But in the respect for time, we'll skip that. But like I said, I'm happy to go through that with anybody. So what we want to do is see how can we use heavy ion reactions, how can we study these things in the lab, and why do we want to do that? And so I think, hopefully, I've already shown you that it's important to understand what the symmetry energy is, but you really can't actually go out and measure the interiors of neutron stars or supernova directly. And so by using these heavy ion collisions, that we can actually get to energies and densities and temperatures that are relevant to that, and we can do this in the lab. If we couple this with neutron-rich beams, we can talk about very symmetric nuclear matter, and we can then reach these areas of interest in terms of the N over Z. Okay, so what do we know already about the equation of state? And this was some work that was headed up by Pavel Yennello, basically taking all of the flow data from many of the EOS and the plastic ball, the lower energy data, higher lower energy data anyway, looking at flow and saying, if we put in place all these different models with different equations of state, can we understand what the compressibility is? What's the curvature of that curve I showed you? Again, at normal nuclear, for the value of stability nuclei. And so they were actually able to constrain fairly well what is the compressibility for symmetric nuclear matter, and the values that they get agree quite well with the giant monopole resonance. Now, the giant monopole resonance is the best way to measure it for normal nuclear matter that's cold and it's at normal density. Okay, the beauty of the heavy ion collisions means you can get away from normal nuclear density and really try and test higher density and lower density. But it's very nice to show that at least here you get overlapping answers. But what we really want to do is look at what happens as we get away from the value of stability, right? Because that's where Ani's interesting reactions occur, is away from the value of stability. And so now we have to take this change in energy with density and actually express it as a function of both density and isospin, or N over Z. And so you have your term for symmetric nuclear matter, and now you have this new term, which is the symmetry energy, which is now a function of isospin, which is defined as the N over Z minus A, or the density of neutrons minus density of protons over the total density. You can look at it here if you look at the energy in terms of the difference between neutron matter and nuclear matter. And if you take the difference between these two, you can extract out the symmetry energy, and often you'll see plots here where you actually see the symmetry energy plotted as a function of the density. And you can see here where we kind of know what's going on. Things converge quite well. As you get out to higher densities, we have no clue, basically. Okay, I'll just say that. We have no clue. But there's a wide range, and actually this is a fairly constrained one. If you look at the typical plot by Brown, they're all over the place, with even just using different Sturm interactions in terms of what is this symmetry energy as you get away from normal nuclear density. I want to point out these two terms because you'll hear them later, and if you ever hear other symmetry energy talks, people will talk about soft and stiff. And in terms of the symmetry energy, when we talk about stiff, we're talking about this being linear or more than linear, okay? So there's a continual rise with symmetry energy with density, and for soft equations of state, they tend to turn over, okay? Now, soft and stiff, everybody has their own model and then has their soft and their stiff, and so those are not unique descriptions. They're relative descriptions relative to soft or stiff within a model, so you have to make sure that you know what they mean. But so you understand what I mean, we're going to be talking about soft versus stiff type interactions. Okay, so that's what it looks like if you look at the symmetry energy, but just to come back to this basic plot, this is mainly here for students, right, is that if you look at the binding energy versus the density, you're seeing this stiff versus this soft interaction. So it's a shift in this curve, in the minimum, and in the steepness of what's going on. Okay, so within nuclear astrophysics, lots of different equations of state are used. A few are ruled out, but there really is a huge variety of things that are being used right now. And so we need to be able to provide some input so that they can use ones that actually make some sense and not just anything that they want. Okay, so what I'm going to do is look at some flow data. Okay, and so the motivation for looking at transverse collective flow as a signature, there's lots of different signatures that you can look at for symmetry energy, and we've done some isoscaling work, and we've done some isospin and equilibration work, and all of that's available at the bar tonight. but for now, we're going to talk about transverse collective flow, which really, I can't do this two-handed thing, okay? So in heavy ion collisions, I'm going to talk really loud, okay? So in heavy ion collisions, if you have a semi-peripheral impact parameter, they'll come by. If you're at low energies, what's going to be really important is this attractive part of the potential, and they'll stick, you'll have a dinuclear complex, and they'll rotate. As you get to higher energies, you get a bounce off. And it's this competition between the attractive part of the potential and the repulsive part of the potential that tells you something about the flow. And if we look at what is this relative rotation, we can understand something about the potential. And that's what we do when we look at transverse collective flow. So, these were some calculations that were done that tried to connect this transverse collective flow to differences in the underlying interaction. And so these were done by Ballonly, and he has 4 different interactions going from something that's very stiff to something that's soft. And then he looks at the neutron and proton flow, and you can see that the flow that you get is related to the symmetry energy that is in the code. Okay? This was also done by a BNV code from the Catania group, and in this case they did something very interesting where they looked at iron 58 reactions and nickel 58 reactions, and they looked at neutrons and protons separately. And what you see for the stiff interaction is that you get a difference between whether you look at the flow of neutrons or the flow of protons, and you also get a difference whether you look at the iron-iron system or the nickel-nickel system. So the flow that you measure is a function of both the N over Z of the particle type you measure and the N over Z of the system that you're looking at. For the stiff interaction, for the soft interaction, you can see that there's very little difference. So again, there's this idea that if we can measure this, we can tell which of these interactions makes more sense. The other thing that the Catania group did is they went from neutrons and protons to clusters. And so they actually then pulled out the flow of tritons and helium-3 clusters and showed that, in fact, for the as-a-stiff interaction, you do have an increased flow for helium-3 compared to tritons. Okay? For the as-a-soft, you don't see it. So this is, again, a signature. For us, measuring tritons and helium-3 is a whole lot easier than measuring neutrons and protons. So it's nice to show that it comes through in the calculation that you still have some sensitivity. So that's our motivation. And that's what we're going to try and do, is look at the flow of intermediate light charged particles and intermediate mass fragments for systems that vary in N over Z, measuring, of course, the fragments we measure isotopically resolve so that we can see what happens to the flow as you both change the N over Z of the system that's interacting, and to look at the different particles with different N over Z coming out. So the reaction, what we did was zinc 70 on zinc 70, zinc 64 on zinc 64, and nickel 64 on nickel 64. So we have 2 systems with a common mass and a different N over Z ratio, and we have 2 systems with a common charge and a different N over Z ratio. So we can look at mass effects and charge effects and hopefully try and distinguish the differences. It's all done at 35 MeV per nucleon at the Texas A&M cyclotron facility. And so we have a K500 superconducting cyclotron. All of these beams were then extracted and run down here to the neutron ball. I'm happy to explain the facility over tequila as well. Okay, so but this experiment, and I've never had tequila before, so I don't know if I'm even going to like it. We did this in the neutron ball, and so the neutron ball, the Nimrod ISIS array is composed of 14 concentric rings. We have full silicon coverage throughout the ball. This silicon coverage gives us isotopic resolution for things up to Z equals 17. Okay, so that's really nice that we can do fragment identification isotopically that high. We can get elemental resolution up to the Z of the projectile. This whole thing is embedded in the neutron ball, and so we can get, event by event, we can get a rough neutron multiplicity. This helps us in doing our event characterization, and if we're reconstructing quasi-projectiles, it helps us to reconstruct in terms of N over Z and excitation energy. For the purposes of this, it will just help us, we'll just use it for our event reconstruction. So our event reconstruction, we looked at lots of different things. We decided to do this in 2 dimensions. So we have the charged particle multiplicity and the neutron multiplicity. And we can cut this up into however many bins we want. But effectively, we made these diagonal cuts And you will see some of the data I show you later labeled as bin 0, bin 1, bin 2, bin 3. So that's just going from something that is very central here, because you have a high charge particle multiplicity and a high neutron multiplicity, to something that's fairly peripheral, where you have a low charge particle multiplicity and a low neutron multiplicity. See how to heat the thing up so much. And we'll have you'll see these little pictures as we go along to help keep that in mind. Okay. In terms of understanding what the real impact parameter is, we ran filtered COMD codes, because geometry and real impact parameter are different things. So in terms of the flow, again, we're looking at a projectile coming in, interacting with the target. In our case, we know we're below the balance energy, so we know the attractive part of the potential is going to be dominant, and we're going to rotate across the thing. And then you will see what effectively is this emission of particles in that direction. And so if you look at our protons from a particular reaction, and you just plot the px of the protons versus rapidity, and you fit through through mid-rapidity, you take the slope and you call that the flow. So that's what you're going to see plotted here. Now you flip the sign because calculations always give you that you're positive, and we know we're negative because we're below the balance energy. Okay. This is just two quick things from previous measurements of other people. This was work done by Gary Westphal and all, where they looked at the balance energy as a function of the mass of the system. So you can see that there's a mass of the system effect involved in looking at flow, and also another experiment where they looked at flow versus the N/Z of the system, and you can see that there are effects of the flow on the N/Z of the reacting system. We'll see these things both in our data, but that's the first thing we want to do, is compare that to our data. And so if we look at Z=1, Z=2 flow, we have the zinc-64 system here. You have, so it's the flow versus the N/Z of the system. You have the nickel-64 system here. And if you go ahead and look at that, you see obviously that as you increase in N/Z, you increase the flow, and that's consistent with the Westphal data. Now, the interesting thing is, if you took that line, because 2 points defines a line very nicely, and extrapolated out, it would say that the flow of our zinc-70 plus zinc-70 system for the Z=2 flow ought to be up here, when in fact it's here. And so what we're seeing here, then, between the two zinc systems, is a mass dependence. So instead of it being where it would be predicted purely on the N/Z, it actually drops because the flow drops as a function of the mass, which is again consistent with the previous Westphal data. So that was really nice. And then we asked the question, well, are these same dependencies there for isotopes as well as just for elements? Because they'd already been seen in the elements. So if we go ahead and look at light charge particle flow in terms of it being isotopically resolved, and now let's look first at our zinc-64 and our nickel-64 systems, which differ in N/Z. And you can see across the board, for any of our isotopes, we get a larger flow for our nickel-64 system. So this is, again, consistent with the idea that you're getting more flow. And there is this N/Z dependence. And now if we go ahead and want to look at the mass dependence, well, we can see the strong isotopic trends. The other thing is to say, one of the issues is we know that you get different yields of protons to deuterons to tritons as you change the N/Z of the system they come from, or the source they come from. So is that difference in is the difference in the flow of the elements due only to different populations of what you're actually making? And we know that's not true, because we see these strong isotopic trends across all of the isotopes. Okay, and you can see across all of them, you see this decreasing trend with increasing with the increasing N/Z. Okay. Now, if we go ahead and ask the question of what about isobaric effects, and we look at our A=3. Okay. So from here for our A=3, we have our tritons and our helium-3, and so they have the same mass but a different N/Z, and you see this clear decrease in flow for the tritons relative to the helium-3. So this is consistent with the prediction of the stiff equation of state from the Catania group, where they said with the soft equation of state, the triton and helium-3 flow should be the same, but with the stiff equation of state, the helium-3 flow should be greater than the triton flow. So now I've given you this stiff and soft. So this is the stiff equation of state from the Catania group, and this is the soft equation of state. So this is what we tend to agree with. So what I want to do, so you can see this decrease in flow across both Z and A for all light charged particles. I want to show you that we looked at some IMF flow as well in the same data. And so this is our proton flow, and we're going to have to calculate flow a little bit differently for intermediate mass fragments because of the acceptance of the detector. So this would be the way you would normally calculate flow, as I showed you with this slope through the center of mid rapidity. We have threshold effects for heavy things. Okay, so for things greater than lithium, we don't have great acceptance backwards. So what we did is we developed a new method where we just take we adjust it, and we shift to 0, and then we take the average of px over this range, and that's analogous to the flow. We have tested this for the light charged particles. So if we do this for protons, neutrons, protons, helium-3, we get the same answer, regardless of which way we do it. When we go to the heavier things, we can only do it this way. So now we do it this way. So that's why here you see this average px rather than flow, because that's what's plotted here. And so now what I'm doing is looking at intermediate mass flow as a function of particle z. So now we're looking at z equal 1, not only z equal 1 and z equal 2, but all the way up through z equal through 9. And 4 now cut into those different impact parameter bins. So here's our central collisions where you have this nearly complete overlap of projectile and target, and here are very peripheral collisions where they barely interact at all. Okay? And you can see that our flow changes across them, and you see again these 3 different systems, your nickel and your 2 zincs. Okay, so we know that, or we expect that